So the topic today is matrix transformations, and the main idea of matrix transformations is, well, it's right here. It's that every matrix defines a function. And more specifically, every n by m matrix defines a function from m-dimensional space to n-dimensional space. And when we talk about matrix transformations, we are talking exactly about these functions. So every matrix actually defines a function. So the plan for today is to show you how these functions are defined, demonstrate some of the properties of matrix transformations, and then from these properties, we see that matrix transformations are what are called linear transformations, and the main result is that the converse is also true. In particular, every linear transformation is a matrix transformation in a way to be explained momentarily. And throughout we'll do examples. Okay, so let's get started. How to define a matrix transformation. So the first thing we need to understand is that elements of Rk in general, so by which we mean k-dimensional real space, should be represented as column matrices. Or column vectors. It's the same thing. So this is not typically how you represent elements in k-dimensional space. Typically, we write the coordinates horizontally. So, for example, instead of, in R2, instead of specifying a point in R2 by, instead of writing that, we write x, y. So elements in R2, this is a picture of R2. You have a copy of the real numbers going across. You have a copy of the real numbers going vertically, and you want to order them. And so x is the first axis and y is the second axis. So you specify a point, like this point here, 2, 1. This is the point, 2, 1. That's how we typically do it. But for the purposes of thinking about matrices as functions, we're going to write that point as a column, 2, 1. So there's still an order. When we write horizontally, we read from left to right. When we write vertically, we read from top to bottom. So the first coordinate is still the 2, and the second coordinate is the 1. So that's how we want to express our vectors as columns. So a point in k-dimensional space. So more generally. Okay, so that's just how we do it. So in Rk, usually a point in Rk is written, so one more time, instead of writing like v1, v2, vk, so usually you have k components for a point in Rk, we write a column v1, v2, vk. So this is, of course, the same thing as a k by 1 matrix. So this thing is a k by 1 matrix. Okay, so that's the first thing we need to set up, is that we're going to express elements in k-dimensional space using columns. And once we have that set up, it's immediate how we can define a function using matrices. So then this allows us to define the transformation of a matrix. So here's the definition now. So definition, let M be an n by little m matrix, then the function, which we write Tm, so this is a function that goes from Rm into Rn, is defined by, so it's a function which eats a point in Rm, and a point in Rm is a collection of m elements, which we write as a column, and we're going to define what it spits out to be the result, that's a capital M here, of doing matrix multiplication m times x1 through xm. And of course, what's going on here? Well, by assumption, this matrix is n by m, and by assumption, this matrix is m by 1. So when we multiply this, the resulting thing, so the actual thing that this is equal to, so this whole thing is actually n by 1. So in particular, this whole thing, so therefore this whole thing is a point in Rn. So that's how the function is defined. It takes this thing here, so you input this is your input, which the input is from Rm, and then the whole thing, this whole thing is what it spits out. And so the output is actually an Rm, so this is the output. The output is in Rn. So indeed, this is a function that goes from Rm to Rm to Rn. Okay, so it's kind of confusing, so you have to remember, so let's just make a quick note. So this is the input, so this is like input dimension. And this is the output dimension. So that's how transformations are defined. So let's just do an example so we can get a feel for how these things are. It's really not too bad. So, for example, let M be the matrix, say, 2, 1, 3, 1, minus 1, 2. So of course this is a 2 by 3 matrix. So this transformation function should be a function that goes from R3 into R2. And how is it defined? Well, so Tm, I keep writing little m, so the 3 coordinates, so points in, we'll write this, these are like x, y, z's, so these are triples, and these things are doubles, so these aren't actual, they're just symbols, so things in here are columns of length 3, input are columns of length 3, and output should be columns of length 2. So if you input a column of length 3, say x, y, z, then what does it spit out? Well, it spits out the product of matrices, this matrix times this column. And when you do matrix multiplication, you get what you get. So 2x plus y plus 3z. So this thing is a number. It's a number that combines three different numbers, x, y, z, in a pre-described way. And the second number it spits out is x minus y plus 2z. So that's what I mean by this transformation matrix. So we can look at some of the outputs. So same example. So for instance, Tm of 1, 1, 1 spits out the number 6, 2. Just using this formula here. So you can input any triple of numbers you want. You can plug in the number 1, 0, minus 1, and when you do that, it spits out minus 1, minus 1. Oops, sorry. So just by using the formula above. So these are functions that input three different numbers. So you input this thing, which is a column of length 3, and it spits out that thing. So, if you input this, then you spit out that. Hopefully I didn't make a mistake. I wasn't thinking when I actually did the calculation. Cool. Alright, looks right to me. So, that is how matrices are to be thought of as functions. So, literally just using matrix multiplication. So you just do matrix multiplication. We can do another example. So, say M is the matrix 2, 3, minus 5, 4, 0, 1. So now this matrix, this is now a 3 by 2 matrix. Put a line here. So the transformation function goes from 2-dimensional space to 3-dimensional space. And how is it defined? Well, if you input two numbers, say x and y, then what does it spit out? It spits out the product of this times x and y. And of course, when you do that, you end up getting a column of length 3. It's namely 2x plus 3y, that's the first entry, minus 5x plus 4y, and the last entry is just y. So, again, it inputs something, it takes two different inputs, two different numbers, and it spits out three different numbers. The three different numbers are, this is one number, that's the second number, and that's the third number. So we're thinking of the first, we have an ordered list of numbers, and we order by descending from the height. So that's what it is. Let's do some explicit inputs. So in this example, we have that, for instance, Tm of 1, 2 is going to spit out 8, 3, and 2. Or Tm of minus 1, 3 is equal to 7, 12, 17, and 3. Just by using the formula. I mean, just by plugging it in. It's already set up over here. You can already see the explicit formula for the function right over there. So that's all I'm using. Oops. So every matrix defines a function. And if it's a 3 by 2 matrix, it goes from 2-dimensional space to 3-dimensional space.